Okay, folks, is there anything we need to talk about before we exactly start? We got a minute or so.
What's happening?
What's that?
What's happening?
What's happening? There's this chair is interesting. You just touch it, suddenly you'll be seeing my back. There's stuff in the news all the time. That's one of the intriguing things about this field. I'm a volunteer at a high school in our neighborhood, and just yesterday I gave a short lecture to the high school students about a new development we will get to later in this class. And yeah, there's no end of news and interesting things, controversy, and so forth. Well, I think it's 1 o'clock, time to start. So here we go. For those who just came in, I do have a microphone on. If you're finding the volume too high or too low, let me know. Otherwise, and video is running, so it should be better than last week where I had to, the video camera had some issues. Okay, so last time we had some questions. That first bullet up there is covers some topics we're going to review, so we remember what we were doing last time. Entry-level cosmology books were a topic of conversation. So I have 3 candidates here that you might consider. Helen Davis is here. She's got some suggestions as well. But let me tell you about mine first. This book is fun to read. It has little cartoons and things in it. It covers more than cosmology, but it does a fairly good job of introducing the reader to the current state of understanding of the key questions in cosmology. So this is not bad. It's might be a little comic book-like for some. It has little cartoons with captions, you know. That one's easy. This one's more challenging. Brian Greene. This is the second of the 3 books he's written for the public, and you have to be concentrating when you read it. He will introduce. Now, let me tell you about the first book he wrote for the public. Introduces the concept of string theory. I would not read that first. I would read this one first. So if you're looking for more of a challenge, read this. The prior book is called The Elegant Universe. Okay?
Yeah.
This is the book they use at the University of Colorado for the undergraduate class on cosmology. It's unfortunately quite expensive. You might be able to find a used one, but the ones that are available to students are $140.
Wow.
But it's full of artwork and so forth. I would defer getting this until, after you've seen this class and decide if this is something you want to get into deeper. But this is a professional book, and modern college books are, as you know, expensive. Okay. Now, Helen has a couple of suggestions.
I'm glad you showed those and the different levels of complexity, because I just Googled, what are the best cosmology books or cosmology for dummies and so on. And so the ones that I mentioned are more, popular, not academic, but probably, the gold standard would be a brief history.
Brief History of Time.
History of Time by Stephen Hawking, and that came out in 1996. And then he did one in 2005 that was updated. It's called A Briefer History of Time. So probably anything by Stephen Hawking.
Yeah, he's also got a newer one that I check out in the library. It's got illustrations.
Yeah, there's an illustrated one too. And then Neil deGrasse Tyson has several. I meant to bring one. I got it it's his latest. I think it's called Astrophysics for People in a Hurry. And however, it didn't have any pictures. It wasn't that appealing. There didn't seem to be any pictures, but maybe I got a library version or something. One thing I found, if some of you know of the website called Goodreads, it's a pretty reliable website about books. And if you go into Goodreads and just say cosmology books, they have a really good listing of about 20, and they're all over the map in terms of complexity, academic level, and so on, and a variety of authors. So that way you could get a good mix. And then there is a dummies book for cosmology, for those of us who need that level. It's called The Origins of the Universe for Dummies, and it was written in '07, but it's a British book, and so some people complain because the measurements are in metrics and so on, but that's one that looked pretty interesting and had some really good reviews. And of course, there's Cosmos by Carl Sagan. He did that one in 1980, and then it was updated in 2013, and that TV show was based on that. A lot of graphics, I think. And then the people that had read the Cosmos from Carl Sagan, they were concerned about, was it updated or not? All the comments on the web were really good about that. And let's see, Stephen Hawking, well, he's got a bunch out there. He's got another one, brief, let's see. Anyway, anything by Stephen Hawking is going to be good. One that I read, it might be the one that you just read, it was his last book. He started it before he died, and his children and his colleagues got it into print. And it's more philosophical, but it's a wonderful book, and he writes so clearly. It's called Brief Answers to the Big Questions, and that came out a year ago. And it's not a very big book, but he writes about the existence of God and how to explain religion and all of that, and he does it in such a clear-eyed way. It was really good, but it's a lot more philosophical than some of the others. And then he and his daughter Lucy have done a series of young adult science fiction. If you have kids or grandkids in your lives, you can get a box set of books that Stephen Hawking and his daughter wrote, and they're like thrillers. They're science fiction, but very appealing to kids. So.
Okay, thanks for that. Was there a question in the back?
I just can't read the author's names above.
Oh, okay, so this one is C-H-A-M
Okay,
and Whiteson.
all right, thank you.
And then, of course, Brian Greene. Another thing, for those who are interested in seeing a different perspective on this, that's pretty up to date, is the series that Neil Tyson did that you might be able to find on some cable channels and stuff, and be able to get that. But it's the original Sagan Cosmos series updated. And I have to say, I'm glad to hear that Sagan's book has held up, because so much has changed since that was published. So, let's see, what's next? Oh, yeah, so my email address is there. Everybody should have gotten an email from me with, obviously, my email would be there. Also, 2 links in that email. One to my website, the website where the lectures are stored, as both PDF and PowerPoint, and a link to my YouTube page where you'll see the videos.
Question here?
Yes?
Or a comment, really. I don't know how many of you have tried downloading your slides. I had a fair amount of trouble until I learned how to do it, and it may help some of you.
Oh, let's hear how you do that.
If you just click on the link that you got, and there's a little icon for each lecture and so on. If you press download, it will do it, but at least the engine that I had to download it, and this may be the same for all of you, it doesn't tell you what's going on. And if you look at the folder on your computer where you tell it to download the item to, it shows up there right away. But that's only the beginning of the download. If you wait like 5 minutes and then say, well, I'm probably done, and you close your web browser, well, there's nothing left in your download.
Yeah, that interrupts the
It's
download.
disappearing. So there's not a progress bar or anything.
Oh, yeah. Well, it may depend on your browser.
Some of these files
So,
are
Cheryl-
big. It
Cheryl-
takes about 5 to 10 minutes on my
It
computer to
told me that it
download.
was gonna
So you just have to
damage.
wait.
It told me that if I tried to download it, it was gonna damage my computer.
It's a virus.
Yeah, it's
Oh,
huge.
that's what
Yeah,
it
the
said.
second,
It's so
the
big.
second lecture
Oh,
is
it's
very.
the second one, I got the first one first.
All right, but anyway, do some experiments, see if you can download if you want to. YouTube, I talked about. So let's do a little quick review. Last time, the key points were expansion of the universe, which was totally unexpected until Hubble actually measured that expansion. More recently, better instrumentation has let us look very closely at the expansion rate, and we see that not only is the universe expanding, the rate of expansion is accelerating. And we think we understand why that's happening now. It's related to dark energy, which we will discuss in detail through the rest of the class. We have new tools for viewing and quantifying space. Telescopes, but not just optical telescopes that we're all familiar with. We have the gravitational wave sensors that have come online, and those are going to be improved. And we have imaging technology now using radio telescopes, which caused a sensation a few months ago when they produced a picture of the accretion disk of a black hole. Some of you may have seen that on the news. I highlighted this, that dark energy, the source of this accelerating expansion, remains unexplained, but there's lots of speculation about that. There is a website, we may get a chance to go here, it's called viewspace.org, and it's a handy little thing for seeing how humans view different parts of the electromagnetic spectrum. So we'll try to get to that today. Maybe, maybe not. So last time we had a bit of a conversation about how to visualize the three-dimensional, four-dimensional structure of space-time. And I took this right out of Brian Greene's book. And essentially what he says, I'll let you read this in the lecture notes. The best way professionals think about the geometry of the universe is to use the balloon, ants on a balloon, and then imagine that we're at the next higher level of dimension. That's the same thing I showed you last week, and that's the way he and his professional colleagues think about these things. It's, if you talk to them about, well, tell me about the geometry of the universe, they are going to go to the whiteboard and start writing equations. The actual visualization in your head is perhaps out of reach for humans because all of our experience is based on 3 dimensions. So I'm not going to read this to you, but I just point out that, in fact, here the word professional appears. Just do what professionals do. Stick with the analogies. And nobody has figured out exactly how to solve that problem, except they start doing math. Okay, we talked about this little video. Those of you who missed last time might want to click on the video. This is part of 3 minutes or so from a Woody Allen movie about the fact that this young child thinks that there's no point in doing homework because the whole universe is expanding and what's the point? And I want to make it clear to you that there's a scale to the expansion of the universe that doesn't affect us, and here's why. Here's a plastic container, and it's made of atoms, and the atoms are hung together by electrostatic forces. Those of you who took chemistry learned all about how atoms and molecules are formed. The expansion of the universe is so tiny in its influence on a small scale that it will not affect this bottle. You can wait billions of years and come back and this bottle will still be the same size because its shape is dominated by atomic forces that are dramatically stronger than gravity. If you look at the universe as a whole and look out 13 billion years and look at how the universe is behaving, at that scale, the expansion is important. It's completely unimportant on this scale, and in fact, even our galaxy is not going to get bigger as the expansion continues. So the doctor, who's not, doesn't appear in this photograph, but the doctor is advising the mother and this young man not to worry about the expansion of the universe. The doctor was right, in between taking puffs from the cigarette. So I wanted to make sure everybody understands, as the universe continues to evolve, the nearby galaxies are going to drift away from us because they are hundreds or thousands or millions or billions of light years away. But on a local scale, there's no impact. Okay, so today our topic is the early universe. And by early, we're going to concentrate on the time from the birth of the universe until we get to 400 million years. Most of this interval is filled with nothing. I'll explain what I mean. The first 380,000 years, very exciting. Lots of stuff going on. And that's what we're going to concentrate on that. But in order to make a linkage to the next lecture, we will extend our view out to 400 million years. I'll show you this graphically in a second. We're going to talk today about the formation of the constituents of the early universe, how we're studying those constituents today, and the significance of the number 380,000. I touched on this briefly last time, but we're going to go into it in more detail today. And we will talk about something called nucleosynthesis, the cosmic microwave background, and the guidance we get from Einstein. So here's a slightly different view of the universe. I've shown you one that goes from left to right, one from the bottom to the top. This one comes from the top down. So we get different orientations. But this is the history of the universe on one page. Here's the Big Bang right there. Then there's this interval, and you see the 380,000 there. So I'll repeat something I talked about last week, but it's worth repeating because it's so important. That in the early universe was filled with particles so small that they are components of the pieces that make up atoms. So if you take a neutron out of an atom and break it into its constituent parts, those constituent parts were the pieces flying around in the early universe because the energy levels were so high that any time a neutron tried to form, it would get hammered by high energy radiation or a particle and scattered into pieces again. So for the first 380,000 years, this area right here of the drawing, the temperature in the universe was so high, the energy levels were so high, that nothing that we recognize today could exist. Certainly no atoms, no electrons, no stars, no people. 380,000 years went by, and the temperature by then had dropped to the point that the pieces could get together and form atoms. So as the universe cooled during that period, electrons, neutrons, protons drifting around could try to get together, and all you need is a proton and an electron, and you have hydrogen. So by the end of this interval of 380,000 years, the universe was filled and dominated by hydrogen and some other components that we will talk about. And then we have this interval here called the Dark Age. And that goes from 380,000 years to 400 million years. Those are the two numbers I mentioned when we started this talk. In this interval, the universe was filled with atoms, but there were no stars. There was gas and dust floating around. And if you don't have stars, you don't have light. So for that, from the birth of the universe until 400 million years, the universe was dark. Finally, at 400,000 years, we have what we call reionization. Stars form, and stars have produced enough energy and energetic light that they can stimulate atoms into different energy states But in the meantime, gravity is working this whole time, and gravity is drawing the stars together, and we begin getting galaxies. But it's important that you understand this interval, 400 million years of total darkness, just gas floating around, but the influence of gravity is there the whole time, bringing clumps together. This will be important later when we talk about some other things, of why the clumping occurred the way it did. So this history takes us to 400 million years, then we have stars and galaxies, and we have the evolution of the universe continuing on to its current age of 13.7 billion years. So I've already talked about what's going on in this period, and that the answer is nothing, just gravity, no stars. Here's the same drawing tilted on its side. So now you have perhaps a more of an understanding of what this area here means. A big bang with a tremendous amount of high energy activity, no atoms, finally formation of atoms, and this patch right here that looks kind of green and yellow, we will talk about this over and over for the rest of the lecture program. Here's the dark age, right in there, and then we get stars, as you see here. First stars, 400 million years, and then galaxies, and clusters of galaxies and super clusters. So today, the rest of today, we're going to talk about this area here. Here's the way things look to the Hubble Space Telescope and some other observatories. So if you're using a ground-based telescope, you can see back to here's present time, 6 billion years, and we go back that way. This is time since the birth of the universe. So ground-based telescopes can see back about this far, and then the atmosphere gets in the way. Hubble produced a very interesting picture called the Hubble Deep Field. Is anybody familiar with the Hubble Deep Field? Okay, well, Judith, can you write a note? We'll show the Hubble Deep Field next week. It's an extraordinary photo, and it reaches back to this time here, 1.5 billion years after the birth of the universe. I actually had a personal experience with the guy who had the idea of doing the Hubble Deep Field photograph. I was on a bike trip with a bunch of astronomers, and it was fun to meet him. He was, at the time, the director of the Space Telescope Science Institute, which is on the campus of Johns Hopkins University in Baltimore, and they run the Hubble Space Telescope and a variety of other telescopes. And his idea, as director, he had, they provided him with a resource that's hard to get, and that is observing time. Astronomers compete for observing time. These telescopes are used for so many observational studies that there's a serious competition to see who gets the time. And Bob Williams said, as director, he would get, I think, 2 hours a month of observing time. That's a big chunk of time. And he said, here's what he told the engineers who point the telescope, here's what I want to do. I want to point the telescope at the spot on the sky where there is nothing. Just nothing. I want to stare at that empty spot, and let's see what's there. And I'll show you that picture. If we have time, we'll look at it today. So let's continue. So Hubble Deep Field really is an extraordinary photo, and then it was repeated in 2004. Now notice we're looking farther back to this interval just after the Big Bang, 800 million years. And then the ultra deep field in the infrared reaches back farther. And sometime in 2021, the James Webb Space Telescope will be launched. And it's a different kind of telescope than Hubble. It sees in the infrared wavelengths where humans don't see. And it should be able to reach back way over here. It should be able to see back so far that it will be looking at light produced when the very first stars might have been born. Because this is, once again, this is the Dark Age. By the end of the Dark Age, the universe had billions of stars, but in this era, the first stars probably started appearing there. once again, as the result of gravity dragging gas and dust